Started out in aerospace engineering, soon moved to search relevance, and ended up getting the opportunity to write a book, which changed my life, and I decided never to do that again. I was fortunate enough to be an early engineering co-pilot, and then I wrote another book, which is ridiculous. So here I am again. And then just recently, a half year ago, I started Arcturus Labs, and of course, please visit us at arcturuslabs.com. To jump right into it, I need to make a caveat. Lexical search is my hammer and the world is my nail. So there's a lot of stuff I'm going to say that's just like in your face, like lexical search is the best. I know it's not really the best at everything, and we'll get to that at the end. But yeah, we're gonna make the best case we can for lexical. And then when I get it wrong, you guys hit me up later and say, there's this other thing too. We could do that as well. I like to learn. But lexical search is everything. All right. I feel very sad because in today's world, semantic search is how you do RAG. And it's easy, right? You take your documents, you chunk them, you stick them into embeddings and get the vectors out. There's plenty of database options for storing and efficiently searching these things. And then at search time, you've got your search tool that your assistant gets, and you do the same same vectorization of the search. It goes to the vector database, you get your vectors out, and it's just easy. And the extra cool thing is that it's not searching based on just tokens, it's searching on the meaning. Because isn't that what you're after, the meaning, the informational need of your users? That's great, but there's problems. Some of the problems are that it is impossible to find exact matches, IDs of products, people's names, stuff like that. If you're looking for a specific phrase that you've heard before, you know it's somewhere in there, you want to have that exact match, but that's not easy to do with vector search. And finally, if you have jargon that was not available, or it's a niche jargon that wasn't in the embeddings training, it's just not going to know it. It's going to give you the wrong answers. Another whole genre of things is relevance is very opaque with semantic search. If you're looking for a doc and you can't find it, there's very little way to trace back and figure out what's going wrong. And fixing it often means training models and doing things that are very challenging and still black box. And finally, and this is one of the focuses, filtering is really clunky. It's hard if you really want to take a big set of data and slice and dice and then do relevance within whatever is left matching. It's really hard to do. And let's take a look at that, because that's the crux of it for me. There's a couple options with semantic search to actually incorporate filtering. One thing that you can do is do the search and then the filter. If you do this, there's a decent chance, if your filter is very constrained, that after all this work, you will have removed all of the items in your search results. And so then what? I guess you go back and get a larger set of semantic search matches. Maybe do this several times. It's quickly going to outgrow feasibility. The other thing's equally bad, just for different reasons. You can filter first and then do semantic re-rank. Now, notice I said semantic re-rank. At this point, you are brute forcing all the vectors to find the closest match. You can't use the same data structures with this method. And if your filter is fairly permissive, then this is going to be a lot of vectors that you have to work through. So this is also uncomfortable as well. So in this talk, I think I've stuck about 2 hours worth of content in the next 40 minutes. We're going to learn lexical search really quick. We're going to talk about how it can be applied in RAG and underscore some of the benefits. But then I'll lower my caveat a bit and discuss some of the problems that are still present for sure in lexical search. And at the very last slide, we'll point towards hybrid search and mostly point to some of my frustrations that I hope the industry as a whole figures out how to solve in the next few years. Let's go. Time to learn lexical search really freaking fast. 3 bullet points: indexing, searching, and results. Now, when you set up an index with most types of lexical search, thinking Elasticsearch or OpenSearch or the Solr, if you're old school enough, you have access to all of the data types that you're comfortable with. It's not just text. You got numbers and it's booleans. You even got some of the more exotic types, bounding blobs and time intervals and compound types. But the star of the show is definitely the text. And in particular, there's keywords, which basically they go in as like categorical values. It's just the keyword. But then there's also text, which gets tokenized and chopped up into little pieces. And that's the secret sauce that makes lexical search fast and accurate in its own way. And to chop up those tokens, we use analysis, a process called analysis. So the easiest way to understand it is to look at an example. The quick brown fox jumps over the lazy dog. The first step we go through is character filtering. This takes that string, doesn't chop it up, but it normalizes it. In this case, all I've done is lowercase everything, but you might remove diacriticals above letters. You might use regex if you wanted to filter stuff out. The next thing is tokenization. A very common thing is just to split on white space and punctuation. So you're just left with the words in the sentences. Stop wording, if you choose to use it, removes all the super common words that don't add much to the meaning. And the most important thing, the secret sauce for improving the recall is stemming, where basically you take verbs, jumps, jumping, jumped, and you chop off the ending. You take same type deal for adjective, anything that has multiple forms, you normalize all the forms. So if you're looking for anything, you can match it. All right. So now since every document in our index is tokenized as a bunch of individual tokens, how do we actually stick it into a very fast index? Let's look at document 43 here, the document that we just dealt with. Every word that we've tokenized gets pulled into a dictionary. It serves as a key for a dictionary, and the values of that dictionary is a sorted list of every ID that token appeared in. And so you can see here how I've highlighted that 43 is in all of these. And we'll get to why this is so cool in just a second when we get to searching. But before we get there, let's take a moment and look at the differences that are occurring so far. With semantic search, docs usually need to be pre-chunked so that you can deal with a very tightly constrained semantic of this chunk. With lexical search, there's no chunking necessary unless you've got books and stuff like that you divide by chapters. Semantic search index can often be larger because these floating point vectors are hard to compress, whereas that structure, the sorted numbers in the inverted index, that can be compressed extremely small. So that has benefits, practical benefits when you're actually serving these models. And the data on the semantic side is fairly opaque, vectors that I don't understand. And lexical search, at least the remnant of the word is there. So once you get down to it, fixing problems is a lot easier to do. Next up is value search. So this same data structure makes it really easy to find things quickly. In effect, we have done all the searches we could possibly do in advance. Consider a search for all Fox documents. That's easy. You just go look at that term in the dictionary, find the vector, and that's literally all the answer to your question. It's not much harder with complicated Boolean searches. So I could do brown and fox. You get those two vectors and you union them together. And fox or dog, similar thing, two vectors, and you intersect them. I said that in reverse order. You union them for, you intersect them for and. But you get the picture. It's really not that hard at all. And the cool thing is, it's not just fast. This is not just SQL, but there are really battle-tested notions of relevance that have been out in the industry for 20, 30 years. Predominantly, the easy way of saying this is all the documents that are in this matching set, whatever vectors you've anded in or together, they are scored as they're processed by TF-IDF. TF-IDF means term frequency divided by document frequency. And those words are a little bit opaque, so break it down one more time. This really means the number of times that a word appeared in a document divided by the number of documents where that word appears. So if you have something like brown fox, and you have a document that has the word fox a lot of times, then that's going to be more important. It makes sense, right? But if brown is in the document a lot, but it's also in all the documents for some reason, we just got lots of documents discussing color, then this term will be decreased in its power to influence the score. So it's an intuitive feeling for how scoring works. When is BM26 coming out? I don't know that it ever will. This thing is really called BM25. That's a slightly more nuanced version of TF-IDF. And finally, whenever it comes to dealing with multiple fields, you can process all this stuff just as easily. It's just as fast. And you can easily weight the strength of the different fields. You can use the different fields as cutoff filters, and it's super fast to process and modify the notion of relevance in these documents. All right, we've accrued some more differences between semantic and lexical search. Semantic search searches by approximate nearest neighbor. It's all vector based, whereas lexical is all token based. I've given you a hint about how it can quickly find the documents with those tokens because it's basically figured that out before your search ever happened. Searching and filtering in semantic search necessarily so far has to take place in different steps, either this before or after. One of the awesome things about lexical search is all these vectors in the inverted index of all these lists of matching IDs, they can be processed in tandem. It doesn't matter if you're really looking for a number or a word or a geolocation, all this stuff through convoluted means gets turned into this list of IDs that is super fast to process simultaneously. Semantic search relevance is a distance. That's your only choice, basically. You can do cosine, but you don't have too many knobs there. Lexical search, in situ, you can change the weighting of fields. You can change the math that is used to evaluate search, and it's really neat to be able to play with it without indexing anything else. And our final chapter in our PhD on lexical search is how the results come back to the users. The obvious thing is the result set itself. I've got these matching documents, and here is how many documents matched, and here is a list of them. By the way, this is the user interface per paper file. It's a good example. What is, I think, really cool when you start thinking about how you could use this for RAG is the aggregations and the analysis that you can do with the matching set. So like right here, I've returned a set of like 3 documents. There's probably some more below the fold. But of the 267 documents, we can quickly run these through and do facet counts to figure out what else might be hiding if we only filtered it down. And you can do anything else if it makes sense in your application. You can do averages of price, max, min, histograms, cardinality, and look up the documentation. It goes really deep. Snippets. I haven't decided quite what I think about this as compared to vector search. With vector search, you have to chunk before you do the indexing oftentimes. With lexical search, you can have the engine effectively pull out snippets that it thinks are appropriate out of long documents. So index the whole document, give me the 5 snippets that are most relevant to this document. And you can concatenate them, glue them together if they're next to each other. But it's not quite as free as what you can do with when you're just chunking by yourself. You can do anything when you're chunking it by yourself. But it's like search time chunking. Highlights, say for completeness, basically if you type anything in, it'll highlight where in the document that appears. It's cool if you type in search and something is like searching, then that should also be matched here. So it does a little bit, but it's not quite as good as vector search of highlighting the sentence that has the same meaning. That's a really cool application of semantic search. Differences accruing. Semantic search, you get back the chunks and the metadata in the result. Lexical search, it's the same content, but divided up differently. You get the full document and all its fields. So that would be its metadata. And if you want to, you get snippets, which might be useful in RAG. But the really cool thing about the results is whereas semantic, you just get the results back. And if you wanted to post-process everything else that might match, that doesn't really make sense. With lexical search, it's just super easy. The data is already there. You can slurp down everything you need to get counts and mins and max and averages. How would you apply that to RAG? All right. So now let's see how this could apply in a RAG application. The first thing we need is a document set as a good example. And for this, I've chosen WAN's Wayfair Annotation Dataset. It's a benchmark data set that came out a couple of years ago for e-commerce products. There's all sorts of home items, appliances, furniture, stuff like that. And it's something that we all deal with this type of stuff. It's not like insurance documents or SEC reports. So just seeing how this works will give you a good feel for how lexical search might be applied. There are almost 43,000 items in this document set, and there's several fields, but the ones that are of most importance to our discussion today are product name, product class, product description, and rating count. On the right-hand side of the screen, you can see, it's not important the details, but you can see where I'm sticking in, I'm creating effectively a schema for our index. Here's the product ID. We're just going to save it as a keyword, no tokenization. Here's the product name. We're going to treat it as with an understanding that it's English. We use one of the canned analysis steps that knows how to chop the ends off English words. Product class, product description, rating count. It's an integer, but it still is going to get stored in that inverted index. And I added an extra one just because I thought it demonstrated an interesting point in a little bit. I pretended that every item in the inventory has an availability, which I'm pretending that there's brick and mortar stores throughout the continental US. And so it lists which of the 50 states are available. So before we do any meaningful search for our customers, we have to already have the data set filtered down. That's one filter that always has to take place. All right, indexing from that is pretty easy. You just take all the documents and bulk upload them to Elasticsearch. So that brings us to search itself, actually making the search. From a API perspective, I'm keeping it really simple here. The search involves a query string from which we derive the actual relevance. There is the availability, which will be filtering out first what state the user lives in. There is the product class, because for each one of these products, it has a word or a list of words. This is kitchen items, this is bathroom items, stuff like that. So there's a product class, minimum average rating, if you wanted to filter out based on, I just want the really high quality stuff. And then number of results, I'm not really going to touch that, but we're assuming 10 results. And probably without going too deep into details, this is how Elasticsearch would allow you to query for stuff. I'll give you a sense about how you would build a relevance query in Elasticsearch. A Boolean search allows you to join a bunch of different terms together. But instead of joining searches with ands and ors, you have these two keywords which have similar effects. Must is like an and. You must, if there is some query in here, you must absolutely match. The document must absolutely match that query in order to be a valid result. But we get to control relevance too. So of this set that must match, we're going to give it bonus points with everything in this should. The things that must match is I'm casting the widest possible net. I'm saying if the user is looking for a blender, kitchen blender, then it's going to look in these two fields. These are very generously analyzed fields, so everything is as loose as possible. We're going to catch as many items as we can here. And then in these bonus point queries, if the document happens to have the exact phrase that the user used, that's an extra boost. If the document matches the exact words that, even though they're not tokenized, even though they're not analyzed and stemmed, if that matches, then that's an extra boost. So ideally, you take the same set from this and you group together the ones that are better matching towards the top. And also TF-IDF is still comes into play. Then there's the filters. If the user has specified, if the API has availability specified, then I add that in as just a term filtered. No scoring, it just cuts off the matches. Same deal for product class. There's lots of different types of filters that you can use. For example, right here, if the user specifies the minimum rating, then we can say, let's look at this numerical field. It's got to be greater than or equal. But imagine any type of filter you could possibly want. It's very permissive. Now, our search results don't get presented in anything pretty, an API, a UI. So we're just presenting them back to the RAG application itself. But it's pretty simple, straightforward. We have a list that goes from here to down there. And here's just one item in the middle of the list. All these fields are probably pretty self-explanatory, but this should give you an idea of how things look inside the index. All right. And the last little bit in our search application before we stick it into RAG is the response. And I really wanted to take advantage for our demo of aggregations. It's really easy to set up. It's specified as part of that same big giant JSON document that you issue with the search. You say, I want to do aggregations, and in particular, for the field product class, I want to catch the top 10 terms. I'm going to do a faceted count over all of the product classes that are most popular within the matching set. And I can present this back to the RAG application is something like this. This is what the RAG app will see. It says that within the matching documents, we have this list of lots of desks, a few other things that are less popular down to top 10. Okay, So that's basically it for lexical search. It's time to shove it into the RAG application itself and to see what we can do with it from here. All right, you guys are probably all very familiar with this type of stuff. Here on the screen, we have the JSON schema tool definition in tiny microscopic text. I apologize. But basically, there are three fields of interest: query string, product class, and min average rating. And that's what the model sees, but when the model actually reaches out to use search, it's going to get something that takes my high-level search, and I've partially applied the function by saying, okay, rather than just searching for anything at all, let's assume that, we're only searching for whatever products are available in this user state. Whatever the RAG application will use already has it filtered down to just states that match. Assemble it into the full RAG application. Pretty standard stuff. The system message, which I won't read aloud here, is basically encouraging the model to be exploratory. It's saying you can do more than one search in series, figure out how to narrow stuff down for the user, figure out what the index looks like for yourself. And then this gets stuck into your typical concierge assistant type application. User says something, the model optionally can choose to use the tool or not. When it's accrued enough information, then it sends that information back to the user, which gets printed onto the screen. All right, so let's look at it in action. Everything you see here, I've typed this in with my hands, but I've got a demo app. So this is analogous to stuff that I saw when I was playing with this application. So we start out with our friendly assistant saying, hello, how can I help you? And our user says, my back hurts from sitting here all day. Now the application is going to use the search tool right now, but it's already doing something that is neat. The search application behind the scenes knows that this user is from Tennessee. So it is already filtered out that the query so that we only get information back from Tennessee. It's none of that filter, then relevance, or relevance, then filter. It is traversing that inverted index all at the same time, and it's going to get the most relevant results that are from that state. Now, whenever it searches, I've seen a lot of different variations. This is one that comes up a lot. It does two parallel searches for two things that really make sense for helping our user: ergonomic chair and standing desk. That's great. Nothing special here for lexical search yet. It also, here's another variation I'll see. It'll say the obvious thing to do for that is a standing desk. And then once it gets results back, it'll read the descriptions and say, okay, there's genres within this, so I'll modify the text itself and look for adjustable standing desks and standing desk converters. It's gathering all the information under its own volition to satisfy the user's request. The cool thing when it comes to how large language models can influence these applications is that the results of this query returns the facet list. So the model itself, and I've encouraged it to take a look at this in the system message, the model itself can actually peruse. I've got these 10 results I can see, but in the remaining results, I've got 553 desks, and then I've got like TV stands that is like 200 something. That's a little weird. And so the model will, when appropriate, choose to do things like filter down just to the things that are more relevant, and it will actually clean up some of the relevance itself. And so then you get to the results. May I recommend the Stantastic adjustable standing desk? So this shows that the model itself can actually learn from the filters and influence what it does. All right, so the conversation goes on in a RAG application. The user says, I only want the best desks. So the model itself can further add more constraints to the search space. And it's at this point, we've piled on three different filters: Tennessee, desk, and the minimum rating of 4.5 stars. So it's a very constrained search problem that if you have any size of semantic search index, it's going to get finicky with like how you keep eking out the performance depending on how you do it. I did not play past this, but one thing that I think would be interesting to try, it's probably pushing the limits of what large language models can confidently do at this point. But as they get better, it might be neat to have them also tune the relevance score. So if the user says, I'm only interested in lower price desks, that's a filter. But if the user says, I prefer lower price desks, then that's a boost. And maybe you could incorporate that into the tools that the model sees itself. But the cool point there is you've got search, and you can just completely change the way that relevance works in situ. There's no notion of having to like reindex or anything like that. All right. There are limitations to my poor hammer of lexical search, and maybe it's hybrid search that will come and save us. Limitations of lexical search. I know that this is a dress, and you know that this is a shoe. It's a tennis shoe. And we both know this is a dress shoe. But Elasticsearch thinks that this is a dress shoe. This has been the bane of my whole career, is trying to convince Elasticsearch that a dress shoe is just a shoe that happens to be shiny and black or brown. Lexical search uses bag words with a little phrase matching if you want it sprinkled on top. But that's confusing, right? If I took every word in my presentation today and I just put it in a box and shook it, you wouldn't really get too much of this presentation. You lose a lot of the semantic there. Lexical search doesn't understand at all that you can have different words that have the same meaning. Lexical search doesn't care that the same spelled word can have very different meanings. If you say not something or never ever in a million years something, lexical search just cares about something, doesn't care about the negation. And there's a lot of context clues that the embedding models will easily pick up. It's what they do that you can't do with just bag of words. These are the very things that semantic search excels at. I think where are we at? Maybe hybrid search can help us. I want filters and facets and boosting from lexical search. I want to be able to take a confusing result and be able to turn the knobs and change the way search works without having to think very hard, without having to change the way that a model, retrain a model. But I don't want this bag of words anymore. I admit it. I want search by meaning, something where I could say, no, really, I want not the penguin. I want dress shoes. I want stuff like that. But here's where we're stuck today, it looks like. Are we really stuck here? Semantic search and filter are filter, then semantic re-rank. Maybe we're stuck here, but at least we're working on it. And just to go through some of the things, one of the things that has actually been around for quite some time, but is friendly to semantic re-ranking, is lexical search plus re-ranking. Basically, you use your lexical search as a filter, and it's filtering everything, but it's also sorting by relevance. So you got a pretty decent set of maybe the top 1,000 or whatever. And then you take that and you stick it through re-ranking. And re-ranking used to be the now old school models of learn to rank, but it could just as easily be something that incorporates semantic vectors. It's the tried and truth thing, but it's super complex. And really, it's just the same thing as this. So it lessens some of the problems with this while adding on complexity. There's another method. I blogged about this recently. I don't think this is the end all, but there's Splade, which is basically a way of taking a language model, let's look at your document and pick out words that kind of like synthetic synonyms. They're not quite synonyms, but they're words that probably should have been in this source text, but they actually weren't in the source text. And they come out weighted. And so you can use this, you can take this big bag of words, still a bag of words, and shove that into your lexical index in another field. This will give you, maybe in your lexical search at re-ranking, this gives you another way of casting an even wider net. But it's still not quite right. You lose the nuance, you lose all the things that you lose with bag of words. And you hit precision by introducing words that maybe shouldn't have been in there. One that was introduced to me 2 days ago as I was writing this course, but looks very promising, is the work that Weaviate is doing with academia with this approach called Acorn, which effectively it takes what is very similar to the navigable small world data structures, or it takes exactly them or something very similar to them. And while it's traversing this structure, it also takes a look at, is this a match to a filter? Seems very promising. I don't think it's been like battle tested yet. And there seems to be like some nuances there, complexity being one of them. I don't know nothing about this, except it's a really cool product idea that has piqued my interest. And I am on the point where I need to go look at this more. But Superlinked is apparently using your embedding structures and using different embeddings for different data types, numerical or text or geographic or anything, and basically taking different embeddings, somehow magically concatenating them into one big vector, storing them on remote third-party databases like MongoDB, and then using MongoDB search, nearest neighbor search, to somehow come back with things that act like filters, act like boost. You can change the boost and stuff. I've thought about how this must happen, and I am fundamentally baffled. So I need to look into it. But I think it's a really cool idea that is at least the combination of semantic search and filtering. It's not one and then the other. All right. So I got through in under 2 hours. Thank you. And I guess, is there any questions?
Great. Let's go over some of the questions on Slido, and then we can go over any live questions we have. Not that many, so I think we can do a good job. The first question from Anonymous is, I found the concept of knowledge graph in AI-powered search book, which is based on indices. Do you have any experience with this in the context of RAG? So maybe it's just semantic knowledge graph in general.
Okay, so I don't know. Is a semantic knowledge graph a HNSW graph of like just the ideas, the vectors? So it's not lexical search. Is it a graph database? If so, it's not lexical search. So I might need to have a little bit more information about what we're getting out of that. I haven't read AI powered search, which is really unfortunate because the co-author is the co-author of my first book.
Maybe we can just bring Doug in sometime and see if he has any comments on this. Cool. Yeah, whoever asked that, just DM me on Slack, and then I can make sure we can see if we can get Doug online. I know he's just working a new job. Within these search architectures, do you often see things like bigrams and trigrams, or has it always been the case that we just use unigrams for better performance?
Oh, it's all the above. Maybe not so much trigrams, but rather than, okay, so what are you looking for when you're looking for bigrams? You're looking for the tokens, but the order of these two tokens are important. So there's two ways of doing that with lexical search. One way is to, when you tokenize, I lied a little bit, and the information about the position of the tokens is also shoved into this super compact data structure. And so you can run a phrase search and you can peel out all the tokens that happen to be one token away from the phrase the 2 gram you're looking for, or 3 gram or whatever. And you can even do cool stuff like slop. You can say this token is 1 or 2 spaces away from that. A lot of cool stuff you can do with phrase searches, but it's a little bit slow too. So one thing that people opt for is, if you're always going to want to look for bigrams, then you take a hit at index time by making your index decently larger, especially if you get into trigrams. But at search time, you can immediately match on those things, and that field can be weighted really high. So yeah, bigrams and trigrams are often used in practice.
Yeah, hopefully bigrams will be able to solve the dress shoe problem, but I'm sure you've seen crazier and crazier cases that make less and less sense.
Yeah, English language
Um,
is full of problems like that.
oh man, I think I could talk to you about that all day. What are some of the limitations and gotchas of things like Elasticsearch and OpenSearch and hybrid search? What other databases do you recommend?
Referring back to my third slide, lexical search for much of my career has been my hammer. And I worked at Eventbrite and built out their search and recommendation system. You can do a lot of really cool stuff with lexical search. At GitHub, my first project before I was fortunate enough to work with Copilot was on code search. So I got to build out the next generation of search 2 generations ago. But I don't know as much about MongoDB and like Postgres. They all have offerings that ostensibly overlap with Elasticsearch and OpenSearch. Now let me read the question again. Is this quite answering what you want? I'll answer what I thought you're asking, and then I see the word hybrid, so I'll modify it in a second. So with you get all the knobs for tuning like relevant stuff. With Postgres, with MongoDB, you're going to get whatever they give you, and you might find that you hit a wall. Now, what are the limitations that got you to open search, hybrid search? What are the DBs do you recommend? When I'm thinking of hybrid search or how I would typically use it, I'm still thinking, betraying my background, I'm still thinking, okay, index everything in Elasticsearch and do some sort of re-ranking. Go to a feature store and get out the information you need. You can do that within the confines of Elasticsearch. They've got amenities now where you can post-process and with a model that you've given to Elasticsearch. But a lot of times, I think people just figure out what they need. They do it outside of Elasticsearch and build hybrid search on their own. And that's a big world. So what gotchas do you have? It just depends what you've actually put together for your hybrid search.
Cool. This question might be, I can probably try to make this more general, but what tips would you have for legal search problems where you're compiling an answer based on information across multiple documents? I guess the more interesting question might just be, are there different ways of improving your search and retrieval based off these domain specific documents? Is there like any kind of pre-training that you can do or anything there? I don't know if this question is.
So I'll make up something. So every search project is alike and different. It's because you're probably dealing with text, or at an extreme case, you're dealing with something that is text-like. It could be like musical notes or geography sometimes. But you're dealing with something that gets tokenized and used as text. You're also dealing with filters. And so I think the 80 percentile of any search problem is getting the box out and opening it and dumping the data into it. Now, when you want to improve information, when you want to improve the application, then there's a number of things that you can do, which gets more expensive, but effectively you start collecting information about what should match as opposed to what like actually is matching. And it's not just gut stuff. At the start, everyone is looking at their pet query and like turning the knob of the boost until they're happy with that query. And then it's whack-a-mole. We realize that the 5,000 queries you haven't looked at have all suffered. But as you get more mature, then you start paying attention to, in e-commerce, you can pay attention to click logging and figure out here's what the users are searching for. You have like your long tail of common to uncommon searches. Here's what to focus on. I've been through Jason's class, so you can figure out these top 10 queries account for 50% of the traffic. Super important to focus on. And then you can look at the clicks and say, every time they see this, they're not clicking on this document ever, they're clicking on this one. You can start using that information to build models to tune it, turn the knobs. And then you can use humans, just brute force humans, have content curators that are familiar with the legal space or whatever space come in and say, here's what you give them the list of common queries and some of the long tail queries. They look through all of them and say, I know the data set is better than anyone. This is the best result. Here's the next. And you can use this information to do things like learn to rank, basically re-ranking type algorithms, train models to figure out how to automatically change the knobs or just resort them brute force. So that's a brain dump of everything I would do for your legal search problem and all the other problems too.
Awesome. Let's jump into some live questions. Vadim, do you have a question?
Yeah, I'm the person who couldn't fit the question to the text box, but I promise it's not that long. So basically, if I take a semantic search pipeline and I reduce the chunk size to one word, right? So every word we embed as a vector, then we pretty much get a lot of the advantages you've talked about, right? Very good exact match recall. We will be able to highlight the keyword. So your argument in favor of lexical search, is it in favor of lexical search or is it just in favor of small chunk sizes?
You've taken a little bit of a hit if you go down to chunk sizes the size of the word, because now you're using a bag of words model because the chunk size of just one word has no context for what's around it. Also, that's going to be a big index. Every one of those chunks is what, 2048 floating points or whatever you choose to embed it is.
Well, we can have smaller word embeddings, but yeah.
Sure, that would be an interesting theoretical thing to do, but I think it would you lose the best of both worlds. Lexical search is going to do a lot better than that because you at least have some context strung together there. Yeah, I don't know. Where do you want to take the idea? I think it would be interesting, but reckless to chunk that small.
Yeah, generally, I would also say that for most of these embedding models, they're not really trained to only embed short sentences. So even three-word phrases tend to perform very poorly. Right? I think a lot of the time when we do embeddings over tweets, because tweets are so short, retrieval ends up being pretty poor. So yeah, I definitely found that to be a challenge, and most times it's actually the issue that we actually want longer chunks rather than shorter chunks. Uzia, next question, I think.
Yeah, thanks, John. I really especially appreciated the idea about boosting. That was something I hadn't really thought about before. That was really cool. I guess my question was just what are some common like softwares or tools that you use? Like you should Paperpile. Like I looked it up. That was cool. Yeah, like any common technologies or softwares that you might want to highlight. Thanks again.
Yeah, sure. Paper pile is interesting because it doesn't actually, it has, it's a
Yeah.
specific search application. It is a very nice way of organizing all the papers that I will never read, unfortunately. I don't know. I don't know. I'm not big into tools and tools. I feel we're all in a space right now that's firmly wearing its sorting hat, and it's trying to figure out what tools are going to be meaningful in the future and what tools are. So in lexical search space, the standbys for me are going to be Elasticsearch these days. Old school, if you go old school enough, Solar was really gross. Everything was XML, but you could actually pull apart the system and reprogram it. So it was cool. I haven't used it so much, but then there are tools for allowing curators to rummage through searches and result sets and establish judgment list of what is good and what is bad is its name. It was built by a company I used to work for. So if you're deep into search relevance, that would be good. Yeah. And then everything else I'm waiting, like when we get back to the LLM side, I'm honestly, most of it, I'm waiting to see what shakes out in terms of LLM evaluations, starting to see some names come up multiple times for LLM application observability, Langfuse, Langsmith, human loop, stuff like that. So there's a bunch of random words. Go and do likewise.
Thanks.
Thank you. All right, let's do one last question. I think we have only 6 minutes left. Albert, do you want to ask your question?
Yeah, thanks, John. I really like the boosting part as well. I had a question about click logs. How do you gain insights from those click logs? For example, if you're for given search results, the users are only clicking, the third result, does that mean your search is off, or how exactly do you formulate how you gain signals from the click logs? And then for learning to rank, what parameters are you adjusting once you get those signals? If you're just doing a lexical search, are you adjusting parameters on BM25, or if you're doing hybrid search, which parameters are you boosting or adjusting?
So for like click tracking, click models, effectively what you're trying to back out of the data is your judgment lists. A judgment list is a bunch of search and document and a score for how appropriate it is. So you take your top most common queries, you take potentially all the documents in your index, you have a curator, and you figure out this is the one they should have picked, or this one, we'll give them the score of 1. This is not as good, we'll give it a score of 2, something like that. That's a judgment list. That's a pain in the butt. Humans are actually not very good at making judgment lists. We just keep throwing them at it as if they were. And so click tracking is basically a way to excuse the humans from that task. And you're doing basically what you would expect. You're saying, yeah, for this search, we've got logs of how many times this search occurred. Every time it occurred, we've got logs for who clicked on what. We can sessionize them. And effectively, you back out, this one occurred, and of the 50 times that it was seen for this query, it was never clicked on. And so that's a little data point. Order matters as well. It's built in, depending on which click model you use, it's assuming that the top is going to be more relevant anyways. And so if you don't click on the first one, it's even more surprising. But click model itself has problems. No matter what you do, you can't get over the human bias that we can't click on what we can't see. And so the most relevant product you have might be top of page 2. And so you can only learn so much through click modeling itself. So this is just the struggle we face. Synthetic data and synthetic judgments actually are a really new, hopeful alternative. They got their problems. The sorting hat is firmly on. We're trying to figure out exactly how large language models judge my work. Now, to the second part of your problem, your question, what are we changing whenever we have these click models and really the judgment list? In principle, you could change anything you want. Like you could parameterize your search to Elasticsearch. You have a weight for certain fields, you have different filters and stuff, and you can optimize that. But what I think people are more comfortable with, and it's more common, is basically you optimize, you get the top results from Elasticsearch, from OpenSearch. And instead of just assuming the top 10 are good, you get the top 100, top 1,000 maybe. It's hopefully sorted so that in the lexical search dumb version of relevance, it's pretty good. And then outside of that, you go to your feature store, and for each of these documents, you get the embedding vectors even. You get anything you want. And what model do you choose to re-rank them? you can choose any model that you want. You can train BERT or fine-tune BERT or something like that. And then you can use methods like Lambda Mart is nice because it's so easy to wrap your mind around. And it's agnostic for the model that you use. It's a way of specifying data to effectively XGBoost would be a great way of implementing Lambda Mart search. It just gives you the data that you plug into it to make it work. So I don't know if that answered the question quite how you thought, but basically it's up to you. Depending on what model that you choose, you can tune it however you want to.
Nice. Yeah, that definitely answers it. What is the second part where instead of adjusting the filters or the boost, you like adjust the model? Is that a specific field or technique, or how can I look more into that? Or just look up Lambda Mart maybe?
That's the word. Yep. Look up Lambda Mart and just realize it's agnostic of whatever model. You can plug in XGBoost or something into the data that Lambda Mart helps you create.
Gotcha. Thank you.
Oh man, I think just hearing the call out for XGBoost kind of threw me back in time a little bit. I feel like these days most of what I've been doing is just to cohere rankers, but you're definitely correct. Like if we have different features, it actually makes more sense. For example, if we have features like price or even some other brand categories, XGBoost probably might work better than these token-based re-rankers. But yeah, I think we're at time. John, thank you so much for taking your time and preparing this lecture. I think I learned a ton about some of the configurations for Elasticsearch, especially the faceting and the boosting. And I'm personally pretty excited to try out how we can use faceting for improving things like tool use in the future. Again, thank you, and we'll see you guys next time.
Yep. Thanks so much, guys.
Take care, everyone.
Thank you.